Yes, I think we can start. So, welcome. It's elective course, new course about Kolmogorov complexity. Um, so it's a bit special course. Um, like Huawei asked to teach a course on Kolmogorov complexity, which is like a very academic topic, and it has very few applications. Uh, so it's a bit strange that the company insists on this. But there are competing companies who are also doing projects, and for this reason, they decided it's priority for them. And so, since I prepared the course anyway, I will first teach it to you because in Huawei they're Chinese students and they have nothing on their face and don't say any. Okay, I'm on YouTube, so but okay, I don't know these people, but they told me it will be hundreds of people, and then there is few interaction possible. So please, each time I say something stupid, you need to warn me and tell that I'm not clear. So and unfortunately, I forget to say important things all the time. And this lecture already started badly because uh, I I need to collect materials from everywhere to make it interesting. And okay, and yeah, a lot of things are in deep research papers or old papers, and then I need to extract like the real ideas and put it together again so that there is a nice story. So it's a big and then invent exercise and so on. Oh yeah, here this is a sheet for the seminar. So today I think the lecture will be a bit shorter. So first, what is Kolmogorov complexity about? So an algorithmic information theory is just a definition on a definition of amount of information in individual bit string, and it's defined as compression limit. We will only talk about it in the third or the fourth lecture. First, I will explain something else. And so this notion appears in many topics in theoretical computer science, but also theory of machine learning and other places, because it's just like a very fundamental concept. And in research, it is overused actually in technical research because because of its simplicity, it can connect different fields. And as things get more complex, more fields come together. And so people are biased to using it. But okay, I'm not going to speak about advanced research, at least not in the first lectures. There will be a few optional lectures about cryptographic result and channel coding and so on. So the first lectures, I will speak about applications to machine learning. And so in the first two lectures, the topic is as follows. So the question is, people in Google DeepMind, for example, they want to, they programmed, they implemented a Go player. And what they wanted is, and this program became very famous 6 years ago. Maybe you remember this. So it was until 6 years ago, any advanced amateur could beat any computer program. But they came up with a program that could beat the best player in the world. So at this moment, there is a player that easily beats all other players, kind of genius, an exceptional guy. And they let their program play against this person 5 games, and he lost 4 of them. And then a month later, they made a new version of the program that beat the old version consistently. And so they did not ask this world player to make a public game again. And so this game of Go is very popular in China. And so it's like football in Europe or something. So many people play it. And but they had a particular philosophy and in programming. This program, they didn't want to tell it anything about the game of Go. They just want a general program that solves reinforcement learning. So reinforcement, you know about reinforcement learning. So you have to pick up rewards from an environment. So that's all the program was designed to do. And actually the same program can also learn how to play chess and other things. So, but then this program was given very specific experiences. So it led, the program was playing against human players and non-human players to increase certain knowledge. And but at least I know very little about the source code, but I know what was the founder was studying. He was studying algorithmic information theory. And how can a machine learn something in a very general setting? And this actually a nice, so a theory for to answer this question also connects to how humans should do science. So this is a very general philosophical setting. So now we're talking about reinforcement learning. Let's speak about sequence prediction. So we receive bits, zeros, ones, zeros, ones, and we want to predict the next bit as well as possible. And so the question is, how can a machine come up with rules that help him to predict the next bit? And so also philosophers thought, like, if humans make experiments, how can they build theories to understand physics and so on and so on? And so there are certain ideas. For example, there was Epicurus. He says that if you have many theories that can explain certain experiment, you need to think about all of the theories. And then there was a conflicting idea by this, I forgot which Greek philosopher, but he said you should only take into account the simplest explanation for what you've observed. And so the theory of algorithmic information doesn't start with Kolmogorov, but actually a little bit earlier with Solomonoff, who tries to reconcile these two ideas. And so let us go. So let us tell what was his solution for Solomonoff. So he said, if we're given a string, a bunch of zeros and ones, and we don't know anything. So what might be a good strategy to connect the next thing, the next bit, so either 0 or 1. And he said, okay, let's consider a Turing machine. So I will explain in detail what it is. It's just computational devices, and you can give it bits, and it will print out bits. And he says, let's give this Turing machine a random infinite sequence. And then let's look to all the trials where it prints the bits we've seen so far. And among them, we will check what has the largest probability of extension, 1 or 0. So that was his idea. It was 1953 or 56 or something. I mean, he was playing with this idea for a long time, and his job was to write grants for airplane company to get money from government. Okay, but I'm distracted. Let's say what so it's clear what his strategy is. So there exists a thing, it's called Turing machine, universal Turing machine, and you put bits in it and bits come out. And so he says, let's make an infinite queue of bits, put it there, and see which bits come out. And among those trials that produce the bits he has seen so far, so that that are available, he checks what has largest probability of extension, and that will be the continuation for the prediction. So that solution, and so idea of Google DeepMind was to use this probability measure to optimize reward from an environment in reinforcement learning. So that's their idea. Of course, there is a little technical problem, like if you feed random inputs to a Turing machine, if this is long, there's a real small probability to find such an X. And then you need to find many of them to estimate the next bits. Okay. Yes, so that's a philosophical introduction. So this lecture and next lecture, we will speak about Solomonoff induction. Then in the next lectures, I will speak about historic word embedding, which will, well, then I will speak about Kolmogorov complexity, what it is, and the first use to solve some problem in logic. So this, I think it will be optional lecture if you would say, I don't care about this. So Gödel proved that there exists a theorem that cannot be proven. So for any proof system, you can come up with any reasonable proof system. You can, or Gödeling proof, at least for most common proof system, you can come up with a mathematical statement that is neither provable nor disprovable within the statement. So this was a bit scary for many mathematicians. So there was a person called Chaitin who also invented Kolmogorov complexity to give a simple proof of this result. And well, when Google DeepMind wants to make a machine that play games, so that they have chess and any game, they also rely on logic. So there's no surprise that these two come together. Okay, that will be another lecture. Then I will speak about information distance. So that's about 20 years ago, 21 years ago. People discovered that many of existing algorithms at this time, so for example, in SVM, you want to insert a kernel. So in machine learning, they for applications, they needed special distances between objects to feed to their algorithms. And what they did is just take all the algorithms and replace the special distances by just a single distance defined using Kolmogorov complexity. And then they were, at this particular time, they could beat, and in some conferences, half of the results that were presented. So this was a very simple algorithm that allowed to take knowledge from one domain, data compression, to machine learning. But then people became clever. They checked what these distances were actually doing, and then they could recombine with domain-specific information to beat this distance again. And then 2 years later, everyone stopped talking about it. So, but we will speak about this information distance, which is just one lecture. And so they created, they did experiments with like the historically first word embeddings. They were created using Google metric. So they wanted to draw from a huge amount of data, but 20 years ago, computers were slow. And so they used the work from Google to do some experiments. For example, automatic translation for unknown languages. I mean, if you have only like a small dictionary, one language, and you get a language where there is very little written, I mean, very little translation available, they were able to like kind of extend the dictionary. by looking at statistics from Google. And again, the idea comes from information theory. And then afterwards, I will speak about the problem of denoising. So extracting a model from data, how can it be done ideally? So this will be the last part. And then there will be a bit harder parts for theoretical. I don't know if there are people who are from theoretical computer science here. Nobody. Okay. There will be lectures, but you don't have to come. And I guess there will be completely different people there. Okay. Yeah, about cryptography. So the question there, do one-way functions exist? Do key agreement protocol exist? I mean, they're used all the time, but there is a mathematical question whether they're safe. And this question has, again, a formulation using Kolmogorov complexity, a pure combinatorial question. Not pure, but okay. So, yeah. Yes, and there's channel coding questions. Okay, so that's enough, blah, blah. Do you have practical questions about the exam? Colloquium. So people who had other courses, for me, I do always the same thing. So there will be a list with questions for theory. And so you need to learn the answers. And then you write it down. And from the way you write, I think whether you understand or not. If I see you understand, it's okay. If I cannot check it, I will ask like, what is this? What is this? Apply to this example, just to check whether you get it through. So then there is exam is just problem solving, like in the homework. So every lecture, I plan to have 2 homework exercises, and there is a deadline every 2 weeks. I don't know how much work are other elective courses. Is the same like obligatory course? Yeah, because I don't know, this is the kind of strange situation. It's already October and the course starts and people choose it, and I don't know anything about you, and I don't know whether you choose it because you want to do nothing or you want to okay. Yeah, please tell me if it's too much work. So okay. Yes, I think that I've told everything for the practical things. So let us now go. So before I start to say what is Solomonoff induction, I will first say what are Turing machines. And we will speak a little bit about which functions are defined to be computable and lower semi-computable. So you can guess here from this very first thing that I explained that we have strings and we need to brute force to evaluate the algorithm. We need to do exponential searches. So all our algorithms will be impractically slow. So the idea of this whole course is to define ideal solutions. If we just want algorithms that halt at some point, but we don't care how long it takes before they halt. And so the general philosophy is contrary to what normally happens in computer science. So people, when they have a problem, they try to make a model for which an efficient solution exists. But here, we will not compromise on the problem statement. We will just say, this is our problem. We will define ideal solution. And then we will be thinking about how to approximate a solution. So in summary, there is a nice quote in how to, okay, so there are some books I should show them. So for comment, this is very nice book by Ian Vitani. There is also so for applications, this is my only chance to. This is the only book that has both theory and applications. Then there is a more theoretical book by Shen and Vereshchagin, both in English and Russian. and I will use it later. And this is from Marcus Hutter, who works in Google DeepMind. And there is a more recent book from a few months ago, but I haven't read it yet. I will, while I'm preparing, I will read it, and maybe we will switch to this other book. So this Universal Artificial Intelligence. But the references, so there is a wiki. So I will put everything I have on this wiki. So if you have a question, then check first if your answer is on the wiki. 6, 7. And I will make lecture notes for every lecture. But sometimes I try to make them before the lecture, but sometimes I will fail, and it will be 1 or 2 days after the lecture. There will be long lecture notes with all the details. So 10 pages, there are recordings on YouTube already. Okay. Yeah. And so our first task is to define what is the set of computable functions. We want to have solutions in terms of programs. We don't care how fast they are, but we need the programs need to halt or at least converge to the right answer. So in algorithms course, you will use a RAM model because you need to estimate time very carefully. But here we want just a solid mathematical answer. So RAM model is very complicated. We will use Turing machines, which are very simple to define, but for measuring computation time, not so good. So that's why we use them. Okay. So it's just for us, it will be really convenient to speak about them. So how are they defined? So there is a computation head, and it can have one of finitely many states. So there will be a set of states. And then there will be tapes. On the machine can modify tapes. You already know about Turing machines. Yes? Okay, then I will very quickly repeat it. So there are tapes. And at each computation, and so every tape has a read-write head. And at each computation step, and so the read-write head is above a cell of the tape, and at each computation step, all the heads read what is in the cell. Then, depending on the state, there will be a write, move, and a write and move operation. So one elementary step is read, write, move. So there will be a transition function delta, and depending on the state and what's on the tape. So here might be an A and a B. It will output what should be written, C and D, for example. Then it should say left or right, for example. For each of the computation heads, it should give different answers. This is a bad marker. I'm afraid at home it's not visible. So it should say for each state how the head should move, and then there will be a new state Q prime. This will be the new state, and then the process operates. And so for example, we can use such a machine to check whether a string is palindrome. Palindrome means that if you write it backward, you have the same word, like in English, kayak. So if you write it backwards, it's the same word. So you can also do this with bits. So in our course, machines always have inputs bits and blanks, or only bits. So for now, for our basic definition of computability theory, we assume that there is a binary program followed by infinitely bits in the input. So for example, we can build a machine consider a machine with only one tape that wants to, hello, welcome. A machine with one tape that wants to check whether the string is palindrome. So then the machine can verify this, but it will do it for a long time because it needs to go back and forth. So the time is number of computation steps, and it will be quadratic in the length of the input to check whether it's written backwards or forward. But if there is a second tape, then the machine can work faster. So the second tape initially is blank, and a machine can work faster by copying the input and then make the heads go in opposite direction. So we will define computable sets and computable functions and variants of computability. So first, let us say what is we say that a set of bit strings is recognizable if there is a machine that halts whenever the input is an element of this set. And if it's not in this set, then it never halts. So I guess I should write it. I wanted to, so there are like very preliminary notes on the wiki with a list of definitions for computability theory. So first, we say that S01 star is recognizable. Sorry, enumerable is the word I will be using. Just to be consistent with the books. So if there exists a machine M, such that for all X and 01 star, MX halts, if and only if X is in X. So this is so then we can define S is co-enumerable. So idea of this definition is like if a set is enumerable, you can also have like an informal machine that has a printer and just print all the elements of the set. And because if we have actually there's an interesting exercise. So why does such a machine exist? So let us speak about a machine that has a special output tape that prints a string followed by a blank and followed by a string and so on. And so the set might be infinite. And so this printing machine might work forever. And there exists such a machine so that whenever S is enumerable, so for every S that's enumerable, there is a machine that on 0 input starts to print such an S. And so what the machine will do is the machine will run all programs in parallel. Okay, I will say more how this happens precisely. It runs all programs in parallel, and as soon as it stops, then the program will be sent to the printer. And so what do I mean with running all programs in parallel? It just means that machine will make a list of all the strings. So first there's the empty string. Then there's 0, 1. So just understand lexicographic order of all strings. And then the machine will run first on the first program for 1 step, then the first 2 programs for 2 steps, and then the first 3 programs for 3 steps, and so on. So I say they run all in parallel. I mean, the machine works sequentially, but it can just distribute its work over many different programs. And so it views the given string as a program, runs it for a certain amount of steps. It stores somewhere a counter for the current index. And then when it's finished, it erases the tape and it goes to the next task. And in this way, machine can check all programs in parallel. And so if a set is enumerable, then we can print it. We can have a printer that creates this infinite sequence of all the elements separated by length. So S is co-enumerable if the complement of S is enumerable. So if 0, 1 star minus S is enumerable. Okay. So sorry for the dry sequence of theorems. I will only do it once in the course. And for all other lessons, I will only define something if I really need it and after I presented motivation. So this lecture will be exception because it's too annoying if I. Okay, and then S is computable if it's both enumerable and co-enumerable. And S is enumerable and co-enumerable. And so if S is computable, then there is also a machine that on input a string prints 0 if it's not in the set and 1 if it's in the set. So how does this machine work? So it's equivalent definition. And so imagine that the set S is both enumerable and co-enumerable. Yeah, it will do the two tasks in parallel. And then we know for sure that one of this is a machine so it will give the same string X to both of the machines. And we know that one of them is held. So it just waits until one of them held. And it runs them in parallel. And the opposite is if we have a machine that prints 0 or 1, depending on if it's in the set, then we have such procedures. And like we first run this machine. So to get an enumerable machine, it runs this machine. If it gets 1, then it goes into an infinite loop, and otherwise it halts. Okay. So this means S is computable. Now let's speak about functions that are computable. So so now let us do I think I don't need the Turing machine anymore. Okay, so now input. So what does fx? We will use functions to real numbers, but they can have natural numbers and rational numbers as well. And x is just any object that has a natural representation in bit strings. Okay, why not? Let's just define, let's speak about bit strings. But here can be rational numbers, natural numbers, but not real numbers. It cannot, a real number, in general, a real number cannot be represented as a finite bit string. Because a real number can be like a random real number. It's infinite amount of information. So we say that f is Lauer semi-computable. So that means that we can approximate f from below. So if all input-output pairs with the output smaller than f, if the lower graph is enumerable. So I will write the definition. So f is lower semi-computable. So if the set xr, for which r is smaller than f of x, is enumerable. Okay, and f is upper semi-computable. if minus f is lower semi-computable. Minus f. And then f is computable, and you guess the definition, right? If it's both lower and upper semi-computable. F is computable. If f is lower and upper semi. And so intuitive definition of f is computable means that you can approximate the value up to any desired precision. And so, hello. So, so there's this little lemma. I will not write it. Well, it's pretty important. Okay, that's right. F is computable. If and only if there exists a Turing machine. So that for all x and k, output for all x and k. So the output is precise up to 2 to the minus k or 1 over k, it doesn't matter. M over k minus f of x smaller than 2 to the minus k. Lemma. Okay, can you see why this is true with the definition? So how do we get the machine? So it works in both directions. So let's just think what would be easy. Probably this is easier direction, right? So we have a function that satisfies this. And now we need to, and let us say that, yeah. And so now we need to come up with lower and upper semi-computable approximation. So we need to approximate this set and the same with this. So let us start with this set. So how can we enumerate this set? If we have a machine that satisfies this. Well, we don't need to, I mean, we can use the definition here. And so we receive a pair x and k. And we need to check, sorry, not x and k. We receive a pair x and r. And we need to halt if its value is lower than the value of the function, strictly lower. So that's what we need to make this set lower semi-computable. Here is the definition. So we want to prove this direction. So we have to prove that this set is enumerable. So we need a machine that gets x and r and halts if this is true. What could the machine do? But we have a machine that's doing this.
Is it the absolute value?
Yeah, absolute value as real numbers. So okay. So the question okay, I didn't specify what's the output of M. So M is a rational number here. So M produces values. There exists M with output and Q. So it outputs a pair of rational numbers.
So if we remove the brackets, m of x and k would be less than 2 to the grade minus k plus f function of x And as 2 to the grade of the minus k is always positive, so we get that the output of function m of x and k is less than f of x. And that means that it's lowers semi-computable.
Yeah. So let me repeat it. And so the plan is to evaluate mx comma k minus 2 to the power k. So that's what you're saying. And so we will wait until this value becomes bigger than r. And if this happens, then we halt. So we know that f of x. So we are guaranteed that this value is smaller than f of x. And if k goes to infinity, it approaches f of x. So if x of r satisfies this condition, then if k is large enough, we will see that this will be at most r. And so if k is large enough, we have that this is at most r, and hence, we wait until it's strictly smaller than r. So now it works. And this must happen. So this is what you say, but then I missed. Yeah. So I can take away this thing. It's still true. And then I place f here and 2 to the minus k here, and we still have this inequality, which is here. Okay, let me place it back. And so we have a function that we have a function that satisfies the definition of this set. And then to check whether it's upper semi-computable, we can do the same. Okay, now let us prove this direction is good. Let us prove the other direction. So we can enumerate this set and the same set for r bigger than x. So dr is enumerable. So now we need a machine that always terminates and outputs a value that's closer than 2 to the minus k. And so here, when I speak about the value of the machine, I assume that the machine must halt. And then when it halts, there is some output on the tape. And so we can use machines to map strings to strings. I didn't clearly say, but okay, we have seen machine, they have tapes, and we can define some output as the contents of one tape when the machine halts. And so we drop the blanks, the infinite sequence of blanks in the end. So we say the machine has output if its tape consists of a string followed by infinitely many blanks. And then the string is the output. And so we can define machines that have output in Q. Okay, so now let us assume that we have machines that halt on this set and on the same set with the opposite sign. How can we get a machine that satisfies this thing, that satisfies this inequality?
Take some x, for example, 0.
Yeah.
And then start these programs, which one also move to that site with that.
Exactly, yeah. So here we use printer version, the printer equivalence. So that's what you say this try all programs, but basically it means you use the printer version. And then you check for all things that are printed, whether the input is X, and you keep printing and printing until you find a value, a lower value and an upper value that's closer than 2 to the minus k of each other. And so you run those two printers in parallel. and then when as soon as you find the best are lower and the best are lower and the best are upper are close enough, you know that F must be in between, and so you can help with the middle or whatever. Okay, so now we understand how we can define computability for real functions. And so we will also speak about probability measures. They can also be computable or lower semi-computable. What are probability measures? They are functions. So we will basically use pre-measures. Okay, so let me say what is pre-measures. We will assign probabilities to strings. So we will use probability. We have 0, 1 star, 2 real numbers that are non-negative. And such a P is called a measure if P, or pre-measure to be mathematically correct, if P of empty string is equal to 0, and for each string, extensions sum up P of X. So this is probability measure. So P, and I will just say P is measure. So this is what I mean. We also have semi-measure. I will soon explain why semi-measures are extremely useful in sequence prediction. So in semi-measure, sorry, not 0 here, this is a mistake. So please, each time I say something stupid, it's important you tell me about it. If you do not do this, I will say more stupid things in exponential rate. So, okay. So for semi-measure, we have inequalities here. So semi-measure corresponds to probability measure. When you continue with prediction, you lose probability. Okay. And so now we did all this computability theory. And so there is a little lemma. It says that a measure is computable if and only if it's lower semi-computable. A measure P is computable. It's the end of the boring computability theory. No, I need to say about universal machine and halting problem. Okay, but first let's a measure P is computable if and only if it is lower semi-computable, and the same for upper semi-computable. Okay. So how can we prove this? So here we have measures, so I put the equality back. Go to one. Okay, so the claim is, so what we have to prove, the measure is lower semi-computable. So we can enumerate all rational values lower than the function value. And then the claim is, if I know all rational values that are lower, I also know all the ones that are higher, because we know that if we have both of them, then it's computable. So, okay. So I give you a string X. So there are two directions. So first, there is easy direction. If it's computable, then it's lower semi-computable. It's just from this lemma. So now we want to do the other direction. So I give you a string X, and you can calculate P of X. You can start to approximate from below. So you can enumerate the rational numbers. They are increasing up to this value. But how can I enumerate numbers that come from above and decrease downward? Well, then we have to look to the equalities here. We know something nice. If we sum up the probability of all the strings of a given length, then their probability will be equal to 1. So another way to write Px is to say that is equal to 1 minus sum of all Px tilde, where x tilde is in strings of, okay, let me write it better. Oh, I see. Okay, so P of X is equal to 1 minus the probability of all the strings different from X and the same length. XC, where length of C is equal to length of X and Z not equal to X. Okay, but then I can use my lower approximation for each of these probabilities. So each of these probabilities are going up. So after the minus sign, this whole thing is going down. And so I have upper approximation. And that means P of X is computable. Okay. And so there are a few things I forgot to tell when I was speaking about Turing machines. So let's say them now. So a Turing machine we can present as a bit string. Why? What is a Turing machine? It's just a computation head and a bunch of tapes, and these tapes are just characterized by their alphabet. So machines can use zeros, ones, and maybe other symbols. It's not really necessary. So 0, 1 blank, there's actually enough, but if you want, you can increase the alphabet. And also a number of tapes. And this, but then the computation head, it contains a transition function. It tells you when it reads a bunch of symbols and when it is in a certain state, to which other state it should go. So, but tape alphabet is finite set. Set of states is also finite set. So a Turing machine is just a finite amount of information, and it can be encoded as a string, a bit string. Okay, so we can make fix an encoding of Turing machines, and then just use a bit string to specify one machine. And so we can define what is called a prefix universal Turing machine, or I call it like this. Prefix such a machine has a following property. So for every other machine, but it's just, okay, let me say it directly. So no. Okay, let me first define what is prefix universal. I don't need encodings for it. But then to prove that it exists, I will use encoding. So machine, so U as a Turing machine is prefix universal. If for every Turing machine M, there exists Q, this bit string, such that for all inputs, let's call it QP, we have that the universal machine on input concatenation of Q and P is the same as M input P. So it's a machine that can simulate any other machine. So standard definition, U has two arguments of universal machine, but for in the course, we always need to concatenate them. So I changed the definition a little bit. Okay, so this is a prefix universal machine. And this is important because we will be able to simulate all machines. And it will be important to understand what is this universal prediction when we run a machine on random input. It means that with certain probability, we will be simulating other machines, but I will explain it soon. Okay. But there was some reason why I explained this. Okay, anyway, so let us speak about a set that is not decidable. So I give all this definition, but we don't have a negative example. And so halting problem is a set that is not decidable. And so, now I understand why I need encodings. So the halting set is a set of pairs, an encoding of a Turing machine, and some input. Let's use Q and some input P. And the correct, so when we get machine Q, input P, the machine halts. So this is halting set. This is an example of a set that's not decidable. Okay, so why is it not decidable? So this is theorem H is not decidable. And this is because of some self-refuting machine. So we prove by contradiction. Sorry, computable. It's the same thing. Yeah, I will. I'm so used to mixing the terms, I will not unlearn this. So H is not computable. So undecidable is not, yeah, is undecidable. It's equal to not computable. Okay, so so let us write down the proof. So assume H is computable. So then there exists a machine that how does it work? Let us create a machine D so that D of P halts. If and only if a universal machine, sorry, if MPP does not halt. I will does not halt. Let's rewrite it by up arrow. Okay, so I claim that if H is computable, then we can actually build this machine. Right? It's easy because we just have to look to the definition of H and set Q equal to P. So then so if this is decidable, we run our decider, we know what is happening, and then the machine does the opposite. If it halts, if MPP halts, it loops, and otherwise it halts. So just doing the opposite of this machine. Okay. So we know that this is for all P. Now let us choose a special P. So we just said that D correspond to real machine and let P be the code of D. So then by definition of D, so dP halves, so by choice of P, if MPP does not halve. Sorry, I already used the definition, but sorry, now I need to use the other thing. So here is the definition. Now I apply the assumption. dP halves, I say that P is a machine that simulates D. So dP halves if and only if MPP halves by choice of P. Of P, and here by def of. And so now we have equivalence. MPP halves if and only if MPP does not halve. So this is the contradiction. So we obtained contradiction, hence our assumption must be wrong. It means H does not halve. So, but maybe you already learned this. Very good. But it doesn't harm, I guess, to repeat it. Okay, so halving problem is not decidable. It will be trouble for us that halving problem is not decidable. Because the consequence will be that the Solomonoff measure will not be computable. Okay, now let us, this is finished now for, this is everything you need to know about computability theory. Oh, sorry, there is one more thing. A function is limit computable if there is a computable function whose limit equals the function. Okay, I will say it again when we actually need it. Okay. So now let us go. Well, let us first get used to the definition of semi-measure. So how can we use semi-measures to make, so let us go back to sequence prediction. Okay, we receive a bunch of bits and we want to know what is the next bit. Very general question. We have no information, only the bits. We want to learn from scratch. Okay, so imagine that somebody proposes a semi-measure over all the bits. And I want to know how many mistakes I make. So here we have our sequence. I'm just writing a random sequence, and I want to know the next bit, 0 or 1. And I'm given a measure P that maps strings to non-negative numbers. P is the measure. So now I will predict the continuation with maximum probability. Px of P, I take the best P in 0 of 1. Doesn't need to be binary alphabet, you can always do this. Now I claim that maximum number of mistakes is binary logarithm of, so now let us have a string x, and let us predict subsequent bits and ask what is maximum number of mistakes that we make. So we are given x, so in the beginning we have the empty string. The question is, what's the first bit of x? And so we need to predict something. Then we predict the second bit, the third bit, and so on. Question is, what is maximal number of mistakes that we will make if we use this strategy? And so our okay, let me write it as this. So our estimate is x1 till xn minus 1 of b. And so now we want to know how many times. So we want to know the cardinality of the indices I, for which the predicted I differs from xi. And I claim that this is smaller than the binary logarithm. So logarithm will always be binary of 1 over p. So here I is smaller than the length of x. So can you see why this is true? So now you need to wake up because something new is happening. By the way, are you from third year or fourth year? Second year? You from? Ah, okay, master, yeah. Okay. So how can we prove that number of wrong predicted bits is at most probability, 1 over probability? Okay, what we know. So there is no computability here. So if you were sleeping in the until I wrote down, no problem. You only need to know what is semi-measure and it's on the board. So answer must come from here. Okay. And so let us look to the predictor. We take the maximal probability here. So what do we know about probability when we make a mistake? When we make a mistake, what happens? We can look to the ratio of, so imagine that at xi we make a mistake. What do we know about this ratio? So can it be bigger than 1/2? If the I bit is wrong, can this be bigger than 1/2? Just look to the predictor. We predict the max probability, which is bigger than 1/2. If we are wrong, it means that the ratio of probability must be smaller than 1/2. So now it's clear, right? Why we have this many mistakes. We start with probability at most 1. And because of this inequality, so since we take the smaller one, we lose at least half of the probability. So if we want to minimize worst case number of mistakes, we can think about the sequence and try to find the largest possible probability. And so that's where Solomonoff came in. And he says, I will use monotone machine and give it random input. So I just say what is monotone machine. Okay, this is just motivation. We don't need it anymore. So monotone machine is machine with separate input and output tape. On the input, it has infinite bits, infinite sequence of bits. And the machine may never halt, and it writes bit on the output tape 1 by 1. So that's a monotone machine. Just Turing machine, it has input tape, output tape, and here are no blanks, infinitely many zeros and ones, and they act as a program. But the head can only move in one direction. It can only read the bits in the program going to the right. The output tape can only move in one direction. So it will write something and then later it cannot change it anymore. Output. And then besides this, the machine can have a bunch of work tapes. So this is not important. Okay. And now Solomonoff defines special measure M for this scheme where he uses, so M of X is probability that X appears at the beginning of the output tape. Probability that output tape in this process starts with X and maybe any continuation. So this is prior distribution. Okay, so should I write this? So we just, okay, I will write it. Oh, X is probability for random input of P from. So there are infinite binary sequences. We take a random infinite sequence and we look to the probability that machine on input. Oh, there is an annoying. So I use all M for machines. I will now use another letter for Turing machine. Let's use it. Let's call it V. Here, that are Turing machine. Probability that V of P starts with X. And note that is a bit strange. Now our machine doesn't need to stop and it has infinite input. But because the computation heads are one way, it can only move to the right, it is okay. We can still define the event probability that on the output tape, the initial segment contains X. Note that after X is written, this initial segment can no longer be changed and the machine continues to compute. Okay, and so now we have a little bit of work. Let's check that MX is a semi-measure. So it's so first probability of any event is at most 1, so this is okay. Second, probability of this is also okay. Probability of event of seeing X followed by 0 plus X followed by 1 is at most probability of seeing X. So we have a semi-measure. This Solomonoff measure is semi-measure. Now, next question. Is M of X computable? Okay, this is even a question. It's not computable. I will prove it soon. But we have something better. Is it Lauer semi-computable? I still have my definition here. And I ask this to you, what do you think? Is M of X? So the function X goes to M of X. Is it Lauer semi-computable? If something is not clear, you need to ask you want me to repeat something. So you're tired from the week, so somebody needs to say something, but not always the same person. Because, yeah.
By the dilemma.
By lemma, you mean lower semi and upper semi-computable provides computable. But I will soon prove it's not computable. But my question is, do you think it's lower semi-computable? And here is definition of lower semi-computable. If I give you a value R that's smaller than the function, can you figure this out? So if I give you a rational value, oh yeah, I should have written, it doesn't matter. So I give you a rational number as just a pair of numerator denominator. But okay, that doesn't matter. Can you figure out that R is lower than this function? So I give you a number R. Is it lower than this probability? Is it lower than the probability that the machine prints X? Well, we can check this. Answer is we can check it. What we will do, we will try all inputs of the machine. And then each time some input prints X, we will record this and check the measure of X. So we will build a tree. So all the inputs are in. Okay, sorry, I thought it was easy question, but I was forgetting that I need to draw a tree and fill it up. So okay, here I make all this infinite sequences B. Those who start with 1, those who start with 0, and so on. 1, 1, 1, 0, 0, 1, 0, 0, and so on. And each time I find the P that produces, and maybe 0, 0 produces X. Then I will understand that probability of getting X is at least 1/4. Because probability that random string starts with K fixed bits is 2 to the minus K. Random sequence, I mean. So here, random infinite sequence. And then I wait a bit more. And maybe I see that this string here, which is 1, 1, 0, also produces X. And if I see this, then I add it to my probability. So I have 1/4. Now I add 1/8. And I do something more. I block all the parallel runs of any extensions of X. Because if later I see, I will of course see that 0, 0, 0 will also produce X, because already after reading the 2 first zeros, the machine printed something with X. So it might print more, but we don't care. That's not our event. And so we go over the tree, and each time we find a prefix-free set of initial programs, starts of programs that produces X. And so we approximate the probability of seeing X from below. So we can lower approximate this M of X. Okay, cool. So let us build a bit of intuition. What might be this M of X? So let us see that this prediction, let us try to understand that this is reasonable prediction. So this is what this Hatter guy basically is devoting his life to, with all the money from Google DeepMind and PhD student and so on. And so the first question is, what happens if we apply the strategy to the sequence with all zeros? So that should be like easy to predict, right? So there is 0, 0, 0, 0, 0, and the question is, what is the next bit? And so we want that this predictor chooses 0 again. And so how can we prove that this makes a small number of mistakes? We want to verify that M of all zeros, infinitely many zeros, is large. And this is indeed the case. This is indeed the case if V is kind of universal machine. So now we can do something like, know that I define this prefix universal machine. We can do something, we can define such a machine that's also prefix universal. So I gave a definition, but okay, I say I will prove something, but it's kind of difficult to prove something because I didn't specify the machine. We don't know which machine. So let me fix a machine. And so that is defined what is prefixed universal. It just means that if we prepend a certain string to the input, then it simulates any similar monotone machine. So, monotone machine. B is prefix universal if let's call the universal one U, if for every monotone Turing machine B, there exists U such that B of sorry, U, yeah, U of Q B, oh, I forgot some. So for every input, for every program sequence, so for every infinite input. So now U is doing the same. When we prepend P, it's doing the same as V of P. So what I'm saying is for every other machine, when we prepend this compiler, so Turing machines, you can think a little bit as compilers. So like you give it a program in C++ and it outputs the same, whatever you've been printing. You can do it for Python also. And so now you can change from C++ to Python if you put a compiler in the front of your program. So something similar can be done here too. So we're given another machine, C++, we can run it on Python if we prepend it with a compiler. And now something interesting happens with this probability. If we apply this probability with prefix universal machine, then this probability will be maximal. So this was discovery, the insight from Solomonoff. So he says, let me repeat it. And so I claim that space and so let us use now the universal machine here. So I will use an index, and here the lemma U is prefix universal. Then for every V, there exists, for every V, we have for every V, we have that MV is bounded by big O of M. So there is a constant factor. And so MU is bigger by up to constant than any other machine. So here for every monotone Turing machine V, we have that this is true. And this is clear, right? Because with constant probability, we will get this initial segment Q, and then we will be simulating V. So any output that is produced by V is produced on U, but just a bit due to the minus Q smaller probability, due to the minus length of Q. And so the constant here, so we will have that MV smaller than 2 to the two to the plus. Thing up. Yeah. Like this. 2 to the plus, so we need to compensate back times mu of x. So it's clear why this is true. For one person, it's clear. 2 people have given up. I mean, completely for the lecture. The person at home also gave up. So, okay. Let me check again. So, this definition is prefix universal. Is this definition clear? So by prepending it, so given any other machine, by prepending compiler, I can simulate this other machine. So then we want to prove this thing. Oh, let us prove this inequality here. Okay, so what is probability that machine V produces X? So there will be a certain choice of infinite input P that produces this X. For each such P, if we prepend Q, we get a program for Q. So we have a finite string P. So remember, there is a tree. The finite string P appears here. That's say the minimal string that. So if we drop something from P, it won't work. So let's take such a minimal P that produces X. Now the same such P will work on the machine U after prepending Q by definition. So every P that produces some X here corresponds to the string QP that produces M here. So the probability, so U is doing the same, but with probability 2 to the minus Q smaller. So then I cancel out this 2 to the minus Q with this factor. And so the same P that works here now works here when I take the scaling into account. And that's why we have this inequality.
Yeah, what is U in this context?
U is compiler for V on U.
And the value of it is the probability?
Yes. So the so here with certain, so on the machine V, we have with certain probability, we will get this program P that gets us X. Now with this probability, and so it will happen with on V, it happens on V, it happens with probability 2 to the minus P that the output starts with X. But on U, we have precisely the same behavior, but we need a string Q and P. And we check the concatenation Q and P with this probability. So whatever thing that makes a V produce X makes QP produce X. And then, but with smaller probability, factor 2 to the minus Q. And so I cancel this out in this probability. It is very logical if everything else is clear. So if it's not clear, tell me what I should repeat. It's okay, we have time. Okay, so now we have a cool thing. When we think about our universal, we will fix a universal machine, and this will fix probability up to a constant. If I take one prefix universal machine or another, we will have this relation in both directions because they're both universal. And so here I assume U is prefix universal and V is any machine. But if both U and V are universal, I can flip them and I have that there is equality, so up to theta constant here. So that means we have defined a measure that's up to a constant factor well defined for all prefix universal machines. And we will use just any such prefix universal machine and get any such measure. Okay, so now we have a nice definition. And there is something cool, because if one machine does something nice, U is also doing something nice, but with constant smaller probability. And practice this constant is not handled, you cannot handle it. But remember, we don't care about practice for now. I will speak about time-bounded versions later, but not now. Not in the first two lectures. Okay, so now let us think whether this definition with universal prefix universal machine is a good one. And so our first sanity check, we give it all zeros. And then if we think that it makes n over 2 mistakes, it would be very bad. When after giving n zeros, we want much less than n over 2 mistakes. But in fact, it will make constant number of mistakes. So it's first sanity check. Why is it happening? Why does it make a constant number of mistakes? So what I'm saying is that if we want to know the probability of having n zeros, I claim that this is bounded by a constant, regardless of how many zeros. Even if we take infinitely many zeros, it's bounded by a constant. And now we have a cool tool. We just have to think about one machine that we can choose ourselves and then apply this property, because we fixed universal machine in U. Okay, so let us think about the machine that just always ignores the input and always prints zeros. Okay, so this machine will print this sequence with probability 1. And so it will make 0 errors clearly. And now we apply this probability, and we see that the universal machine assigns to the all zeros positive probability. So the probability doesn't drop when we add more and more zeros here. I mean, it's bounded away from 0. And so we know that number of mistakes, oh, I deleted it, it's logarithm of 1 over the probability. So logarithm of constant is constant. So if we give it all zeros, it will make finitely many mistakes and then be correct. So another thing that it can do is if we consider okay, good. So imagine that we have experiment, and there is some rational number of balls. Imagine we have a huge universe of balls, and we take a random one, and if it's red, then we say 1, and otherwise, if it's black, we say 0. And we put the ball back, we mix them, and so on, and we keep doing this. So this is another example on how to generate this. Now, in other words, we generate ones according to Bernoulli variable, right? But the probability, so we will now take some number R that is rational. And we say that for each next bit, we say that probability xn given x. Okay, we now say that probability of seeing x1 xn divided by probability of x followed by 1 always equal to R. So we say we just have independent trials. Each next bit is equal to 1 with the same probability R, and R is rational. Okay, so now the claim is that okay, this example I cannot give yet. So now there is a question, how fast will a priori probability converge to this R? And so what, yes, yeah, the probability that the next bit is 1. Yeah, but I'm really sorry, it's too early to speak about this this next sanity check. Let me look to what I should be, what I can, because it's maybe time to stop. It's already a long time. Oh, and I didn't say why measure is computable. No, not computable. Okay, let us do one more thing. Then the seminar will be a bit shorter, it's no problem. So I claim that if we have a computable measure, then this is also true. Then a priori probability will be bigger. So here is a little lemma. If P is computable, then P is bounded by order M of U. I can drop U because you can agree that it will always be any universal Turing machine. So let's drop it. And let's just define it as a priori probability, it's called, or Solomonoff prior. Okay. So why would this be true? Well, I claim that if P is computable, then there exists a machine V such that M of V equals P. And so this will directly imply this by universality. So why is this true? But this is kind of not so surprising, because when you have a randomness generator, if you randomly sample according to the probability distribution, you get a program that samples uniform randomness and then generates strings according to the probability measure that you want to generate from, right? So so what's happening here is P gets uniform randomness, and then it will just look for a given length of the strings at the cumulative probability and see when this uniform randomness exceeds the first place where this uniform randomness exceeds the cumulative probability. And then it will output these inputs. So if you ask n inputs from the output, so machine V, it needs to think how many outputs it will give. And it will just calculate cumulative probability with sufficient precision, and then arrange the bits. So we will have, okay, let us look on the tree. But that's just how any sampler works. So let us look to all the output strings. Again, 0, 1, 0, 0, 0, 1, and so on. And so we can look to, so here we have P0, we have P of 1. And so the machine needs to decide whether the first bit is 0 or 1. But we'll just check whether this random value P here, small p here, is bigger than P of 0. If it's bigger, it will go in this branch. If it's smaller, it goes in this branch. So let us say that this value lays here. So here is P0, and here we have 1. Oh, sorry, this is impossible. So it will generate this random P, and then look, where is P? And here it will do the same. So it might be that, so then at the next level, we have cumulative of cumulative probability of 1, 0. Okay, my picture is not clean, but you understand it, right? No, not. Yes,
P equal small.
Yeah, small p is random input of machine V. So p will be uniformly random. And so it can sort the strings of given length and then look to the first point where cumulative probability is bigger. Sorry, the last point where cumulative probability is smaller than P. So it ranks the strings here. 0 up to 0, 1, and so on. But like, and so we can look to the cumulative probability for strings in lexicographic order of fixed length. But you never programmed the sampler yourself. Okay, I need to explain it. So okay, let's explain for the first bit. So imagine that P0 equals 1/3 and P1 equals 2/3. Okay. And now I generate a random P. So P needs to decide about the first bit. Then it will say if P is smaller, if P is at most 1/3, it will print 0. If it's more than 1/3, it will print 1. And then the first bit is correct with probability 1/3 or 2/3. And then it can do the same thing for the second bit. So let us say, so I make the 3. So now we have 1/3 for 0 and 2/3 for 1. And then we split again. So we can, for example, 1/9 and 2/9 here. 1/9 plus 2/9 is 1/3. And here, let's say, so 1/27, and here, okay, I need to do some complex math. 9 times 2 is 18, 17, 27. And so we do the same thing here. So to know the next bit, so let us say that P is equal to, so if P is smaller, so if P is above the sum of these 3, then we answer 1, 1. if P is above these two, but smaller than the sum of these three, we output 1 here. Sorry, 1, 0 here. Right, and so we have the intervals. And so we split. We have 0, 0 if you're smaller than 1, 9. We have 0, 1 if we have 1, 9 plus 2, 9. So if we have between 1, 9 and 1/3, 3, 9. And then we do the 3, 9 is 9/27. So when we are between 9/27, so 3, 9, when we are between 3, 9 and 10/27, we will say 1, 0 and so on, right? So then we know the second bit and we can continue. So it just, general programming technique. And if we apply this technique, we obtain a machine that generates outputs precisely according to the measured P. So if P is computable, we have a machine V that computes, that samples precisely according to this, this distribution. And then we apply compiler tier, this universality property. So whenever P is computable, we know that universal measure is larger. Okay, I will repeat this in the next lecture because it's pretty important. And so now let's have a break and then let's look to the seminar exercises. So there is a homework, but I will move one question, the second I still need to make, but this one question will go to next week and we will train a bit more in understanding the Solomonoff measure. Next lecture. Okay. So.